Hello there, Mr. Sutton bringing you this lesson on transforming Maclaurin series. In this one, we're going to be constructing Maclaurin series by transforming known series. In this lesson, we offer an alternative approach to what we saw in the last lesson for constructing Maclaurin series. Because we often have to build a series from a function with an e to the x, a sine of x, or a cosine of x, it's usually more efficient to just memorize and modify the original series rather than building it from scratch when you have one of these functions. So on this page, we're going to write out a few of these basic series, and then we'll work with them on the next few examples. So e to the x, this is actually a pretty quick one to get on your own. If you do f of 0 here, you've just got 1. And then all of the derivatives of e to the x are also e to the x. Plugging in 0 to those just gives you derivatives of 1. So we have 1x, 1 over 2 factorial x squared, 1 over 3 factorial x cubed. In general, 1 over n factorial times x to the n. Sine of x is another good one to have in your toolkit. So this one ends up being x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And by the way, if you're wondering why it's like this, every other derivative of sine is a sine, which sine of 0 is just going to zero out that term. And then all the other derivatives are cosines that are either going to be just positive cosine or negative. So that means when you plug in 0, you're either getting a positive 1 or a negative 1, and it just keeps alternating. So this general pattern here, we're going to have negative 1 to the n power, so that our first term is positive. And then we just want the odd exponents. So we're going to have x to the 2n plus 1, and we have the 2n plus 1 factorial. So this is sine of x. This is another really good one to memorize. For our next one, before I just give cosine to you, I'm actually going to show you why it's cool to have these other things memorized. It turns out we can actually come up with the series for cosine, and here's your warm-up, by writing the series that we get when we differentiate sine. Pause the video and give this warm-up a shot. All right, so if we take the derivative of both sides of this equation up here, derivative of sine is cosine of x. Derivative of x is 1. And then this next one, we're going to have 3 times 1 over 3 factorial. That cancels out the 3's, leaving us with just a 2 factorial down there. So this ends up being minus x squared over 2 factorial. For this next one, multiplying by 5 cancels out the 5 at the head of the 5 factorial. So that's just going to be x to the 4th over 4 factorial. And there's a pattern here as well. This is still alternating, so we still have negative 1 to the n, but now we just have all the even exponents, so it's just going to be x to the 2n and 2n factorial. And in fact, if you use your power rule on this general term, that means we're multiplying by the exponent 2n plus 1. That cancels out the 2x or the 2n plus 1 here, leaving us with just 2n, and this then ends up being our general term. So you can very quickly get cosine from sine, but this one pops up enough that it's also good to have this one memorized. For our first real example here, they're going to ask us to write the first 3 non-zero terms in general term of a Maclaurin series for this function. Now, you can see if you're trying to build this one from scratch, this is going to be a huge pain. Every time you take a derivative, at least the first time you've got a quotient rule, you've still got a chain rule that keeps kicking this x squared around. So that's going to be awfully annoying. So instead of doing that, we're going to take the sine of x series and transform it into this. So we're going to start by writing down the parent series, which is sine of x. Pause the video and see if you can remember what that was. So that was x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And then we have that general term, which is a little tougher to remember, but that was negative 1 to the n, and then we had x to the 2n plus 1 over 2n plus 1 factorial. All right, so that's our basic series. Now what we're going to do is just transform this series one change at a time until sine of x looks like sine of x squared over 2x. So we're going to start by dealing with the sine of x squared. When you have things being plugged into the original function as inputs, it's good to take care of those changes first. So we're going to see what sine of x squared looks like. So in this situation, all you're really doing is substituting whatever this input is for the x here. So instead of x, we're going to have x squared. Instead of x cubed over 3 factorial, we're going to have x squared cubed over 3 factorial. So literally just swapping out x for x squared. And then pause the video and do the rest of them here. So here we've got x squared to the 5th over 5 factorial. And this is x squared to the 2n plus 1 over 2n plus 1 factorial with the negative 1 to the n out in front. Now, at this point, you might be thinking, well, algebraically, I don't need to simplify things in general on a free response. But this is a little bit different of a situation, because it turns out that although coefficients don't need to be simplified when you're writing out Taylor polynomials, variables do. We're not allowed to have a final answer that has, for example, like an x squared to the 3rd in it. We need to turn this into x to the 6th. So we're going to go ahead and simplify all of this. So I recommend you simplify variables as you go. Because you're going to have them simplified at the end anyway, it just makes the whole process easier if you just do this as you go. So this is going to be x squared. This will be x to the 6th over 3 factorial, and that's negative, plus x to the 10th over 5 factorial. And over here, we're going to also do the general term. So we're just multiplying by an exponent of 2 here. This is negative 1 to the n, x to the 4n plus 2 over 2n plus 1 factorial. All right, so this is the simplified version of sine of x squared. We only have to do one more thing on this problem, and that is divide by 2x. So when you're dividing the output of your original function by something or multiplying by something, you're just multiplying or dividing the entire series term by term by whatever the divisor or multiplier is. So for example, this is really x squared over 2x, which is just going to be, and we'll just simplify this right away, that's just going to be x over 2. Pause the video and do the rest of these terms. All right, so we have x to the 6th over 2x. That's going to be x to the 5th over 2. But you've really got 2 times 3 factorial. And I'm not going to bother simplifying that because that counts as a coefficient, so I don't really need to simplify that unless there's a really compelling reason for doing so. For this next one now, I've got x to the 10th over 2x. That's x to the 9th over 2. And we still have a 5 factorial down there. Over here, this is going to be, let's see, x to the 4n plus 1 if I divide that by 2x. And I've got a 2 down here times the 2n plus 1 factorial. There we go. On this problem, they want the 5th order Taylor approximation of f of 1.5 using negative 2 cosine of x. So 5th order, that's 5th derivative. That would be a real pain if we were just doing this from scratch. Pause the video and see if you can use the Maclaurin shortcut for cosine to build and approximate this thing. All right, so cosine, let's write out the original series. That's going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And let's just go out one more just to be on the safe side. So minus x to the 6th over 6 factorial. But they're asking for the 5th order, so we're not going to go out any further than this. Now, for negative 2 cosine of x, that's approximately going to be equal to the 5th order polynomial for this thing. So I'm basically just going to take all of these things and multiply them by negative 2. So this 1 becomes a negative 2. Next, we've got plus 2x squared over 2 factorial minus 2x to the 4th over 4 factorial. And I actually don't need to keep going. If I'm looking for 5th order, 5th derivative, that would be x to the 5th I'd be looking for. But that got zeroed out just because of the way cosine works. So we don't need to go to the 6th power. We just need to stop here. All right, so at this point, all we have to do is plug in 1.5 to approximate f. I'm going to say f of 1.5 is approximately p sub 5 of 1.5. And I actually had to define p sub 5 up here before I could plug anything into it. But now that I've done that and we know what p sub 5 is doing, I can just plug this in my calculator without actually showing all the places I'm plugging in 1.5. So let me do that. So here I am in my y equals. I'm just going to put this whole thing in here, and I'm not even going to bother simplifying it. Let me quit out of there now. Alpha trace y1, and let me plug in 1.5 to get a value of approximately negative 0.172. We'll just do one more example. In this one, we just want the coefficient of x to the sixth in the Maclaurin series for all this craziness. Pause the video and get as far as you can on this one. All right, so hopefully you didn't try building this from scratch. We can just use the e to the x series here. So again, that was 1 plus x plus x squared over 2 factorial, x cubed over 3 factorial, so on and so forth. So if we want x to the sixth coefficient, we're going to have to build this out to that distance here. But we don't have to write out necessarily everything out to x to the sixth here, because the very first thing we're going to be doing for this transformation is plugging in 4x squared for the x here. So let's go ahead and do that. That gives us just 1 for that first term still, and then we've got 4x squared for the next term, and then I'm just going to simplify as I go. So if I square 4x squared, that's going to be 16x to the fourth that ends up in that numerator. And then if I cube 4x squared, that's going to be 64x to the sixth in that numerator. Still have a 3 factorial down there. And I could keep going, but I notice here that I now have an x to the sixth term in my transformed polynomial. So this is probably going to be good enough. The only other thing I need to do is now subtract 2/3 x to the sixth. So let's go about doing this. Now, if you're just subtracting a single term, that's a much easier transformation because you're not going to be modifying all these different terms here. It's just going to be, you've got this whole series, and whatever that is, you're taking away 2/3 x to the sixth. So normally I would write out a bunch of other things and just kind of throw this on the end, but since I only care about the coefficient of x to the sixth, I really just need to write out the x to the sixth term from this last series. And I'm actually going to simplify this a little bit. So 64 over 6, that really reduces to 32 over 3 x to the sixth. So I'm going to write a dot, dot, dot plus this to show that there's some terms I'm leaving out. And now I'm just going to subtract this term from there. And I'm going to write a plus dot, dot, dot because there's a whole bunch of infinite terms that I'm still leaving out. But now what is this? Well, I have a common denominator already. This is just going to be 30 over 3 x to the sixth, which means that my coefficient of x to the sixth is just 30 over 3, or 10. So hopefully this lesson was a transformative, time-saving experience for you. Till next time, Mr. Sutton signing off.